Okay, ladies and gentlemen, so we're going to try to do another video today. We'll see how it goes. So the next lesson that you're going to put into your notebooks is lesson 1.4 and 1.5, which is going to talk about the distributive property and equations. Again, at the beginning of the year here, we're going to smush some of the lessons together because these should be mostly review, things that you have talked about before. So in your notebook, again, you're going to have the title at the top of the page, and then you're going to get ready for some vocabulary. You do not need to write down these skills, but I wanted you to have a heads up here. What we're going to be learning today is we're going to interpret parts of an expression, such as terms, factors, and coefficients. We're going to use the structure of an expression to identify ways to rewrite it. Again, didn't fix my typo yet. And we're going to make sense of problems and persevere in solving them, and look for and express regularity in repeated reasoning. So very similar skills that we talked about in our last video. So let's talk about some vocab. The first term is the distributive property, what this whole lesson is about. The distributive property is a property that can be used to rewrite an expression without parentheses. So it's how we use our little rainbows to get rid of parentheses. A constant is a term that does not have a variable. So a constant is a number. A term, which we already defined in lesson 1.1, so you don't need to write it down again. But a term is a number or the product of a constant and a variable. Just a little refresher. Because today we're going to talk about like terms. Like terms are terms that have the same variable raised to the same power. A coefficient is the number multiplied by a variable in a term. So we'll have a constant in front of our variable. And our final vocab word is simplest form. When I'm talking about the simplest form of an expression, I'm talking about an expression that has been replaced by an equivalent expression that no longer has any like terms that are separated or parentheses or other grouping symbols. So simplest form, we also use that same term when we're talking about fractions, but today we're talking about the simplest form of an expression, not the simplest form of fraction. Pause here so you can get these terms written into your notebook. Remember, you do not need to write this one down because it should be in your notebook from 1.1. When you're ready, press play. And we're going to talk about the distributive property. So just like on our order of operations, we have some information here that I want to give you about the distributive property. When I'm talking about the distributive property, for any numbers a, b, and c, a times the quantity b plus c is equivalent to a times b plus a times c. So what we're going to do is we're going to use rainbows to show that. This tells me that I have a times b plus a times c. I need to multiply this coefficient out in front by every unit within, every term that's inside my parentheses. The same thing happens with subtraction. It does not happen with multiplication. If I have a, b times c plus d, I have one term here because that's multiplication. This is a single term. So I apply that coefficient to every term within my parentheses. Erase that off for a second. One thing with subtraction, negative signs can get confusing. I am an adult and I still get confused by negative signs. So what I like to do is I like to always deal with addition. What that means is when I'm talking about addition here, that really is the same thing as a times b plus a negative c. I want to remember that that negative, that minus, is really attached to that second term. I'll give you an example here in just a minute. So I have my distributive property. Now let's practice. First thing I want to practice is I want to simplify an expression using the distributive property. I don't know why C popped up first. Let's start with A, seeing as they tend to get a little bit more challenging. If I look at A, I have 2 times the quantity x plus 6. Just like I saw with my variable expression, I want to take that coefficient and apply it to both terms inside the parentheses. This tells me I have 2 times x plus 2 times 6. Now I can simplify this expression a little bit farther. 2 times x, in algebra I would just write as 2x. 2 times 6 is 12. And at this point I'm done. I can't simplify any farther because 2x and 12 are not like terms. To be a like term, it needs to have the same variable raised to the same power, and 12 doesn't have any variable attached to it, so it is not a like term. B, my second problem here. Now I've got some subtraction. This is where things get a little more complicated. I don't have a purple pen. With this one here, the first thing I want to do is I want to take that inside minus 7, and I want to turn that into plus and negative 7. That helps me keep track. That negative is really attached to my 7. I don't want to lose it. So what I'm going to do is I'm going to take this minus 2 and I'm going to apply it to my parentheses here. And I get negative 2 times 4x plus negative 2 times a negative 7. When I look at this here, this is one term, even though there's, my goodness. I'm going to pause for a second. And my projector overheated, but it looks like we're back now. So, when I'm looking at this one here, now I can see where my negatives are, but when I apply this negative 2 to this term, it's one single term, so I move it as one unit. So now I have negative 2 times 4x, which gives me a negative 8x, plus a negative 2 times a negative 7, which gives me positive 14. And at this point, I've done all I can do. Things that I have left are not like terms, so I'm done. Now what I want to do is I want to show you what that looks like if I didn't do that plus and negative. I should still get the same answer. If I take this from this step here, let's change colors, and I'm going to move through without changing anything, I still get negative 2 times 4x minus negative 2 times 7, because if I leave that minus there, then this 7 is really positive 7. So I get negative 8x minus negative 14. I wind up again with that double minus. Minus a negative is the same thing as adding a positive. 8x plus 14. I land in the same spot. I get the same answer no matter which way I do it, but I think it gets complicated to see those minus a minus, and I think it's easier to go in and change it to add a negative. Up to you. As long as you can get the correct answer, I don't care how you get there, as long as it's mathematically legal. So now let's talk about this last one here. I have 3x minus 7 times the quantity 3x squared plus 4. So for this one here, again, I'm dealing with negatives, and I don't like negatives. So what I'm going to do is this minus 7, I'm going to turn it into a plus a negative 7, just to remind myself that that negative is really attached to the 7. To get rid of these parentheses here, I take my negative 7 and I'm going to apply it to the pieces inside the parentheses. So 3x stays the same, plus a negative 7 times 3x squared, plus a negative 7 times 4. On my next step here, I need to get rid of my multiplying pieces. So I've got 3x plus negative 7 times 3x squared gives me a negative 21x squared. That squared is only applied to the x. I don't need to do anything with the 3. Plus a negative 28. Now at this step here, I don't have any like terms, so I'm done. I have x raised to the power of 1, and I have x to the power of 2, and I have a constant. So there are no more like terms. The only thing left that I want to do with this expression is when we write out our algebraic expressions, we tend to have the symbol that has the highest power first. So I would rewrite this as negative 21x squared plus 3x plus a negative 28. Same thing as this, I just used my commutative property of addition to bump these guys into different spots. This is correct, and if you gave me this answer on a test, you would be marked correct, but this is just a little bit more correct. It's the way that we would write it when we see it in an algebraic equation. So, lots of different things that we can do to simplify with our parentheses using distributive property. On to our second section of this lesson, we're going to talk about equations. And like always, we're going to hit those quick skills so we know what we're going to be learning in this lesson here. You do not need, I don't know what is going on with my projector. There we go. You do not need to write these skills down in your notebook. I just want to give you a heads up about what we are learning. We are going to create equations and inequalities in one variable and use them to solve problems. And we're going to solve linear equations and inequalities in one variable, including equations with coefficients represented by letters. And we're going to work on the math practice of constructing viable arguments and critiquing the reasoning of others. So, vocab, get your notebooks ready. In the vocab here, we have, the first term is an open sentence. An open sentence is a mathematical statement with one or more variables. It's what we call an expression. Next, we have equations. An equation is a mathematical sentence stating that two expressions are equal. So if we take our two open sentences, or our two expressions, and we put an equals sign between them, we wind up with an equation. Now sometimes that expression might be a single number. Our open sentence might be a single number, or it might be an expression that has multiple parts, that has letters, numbers, and operations. Solving. So the process of solving is finding a value for a variable that makes a sentence true. When we're talking about solving, we're talking about finding solutions. A solution is a replacement value for the variable in an open sentence that makes the equation true. So when I'm talking about solutions, I can have one solution. If I have x plus 2 equals 4, I know that x is going to equal 2. That equation has one solution. But I can have equations that have infinitely many solutions, or I can have equations that have no solutions. If it has infinitely many solutions, it winds up being something like x equals x, or 2 equals 2. If I have the equation 2 equals 2 at the end when I've simplified, no matter what I put in for x, 2 will still equal 2. The other thing that can happen is I can have no solutions. When I go through my process of simplifying my expression, I can wind up with a false statement. Something like, at the end of simplifying, I have 2 equals 7. Well, that's not true. No matter what I do to x, 2 does not equal 7. So in that case, I have no solutions. I have no replacement values for a variable that would make the equation true. We'll practice. Last one is an identity. The identity is an equation that is true for every value of the variable. So if I wind up with an identity at the end of my simplification, that means that I wind up with infinitely many solutions, where I have the solution set is all real numbers. Vocab. Again, these ones don't need to go into your notebook, but we're going to talk about what it looks like here. Go back real quick. For these ones here, replacement set, set, element, and solution set. I will be using these terms and you will need to understand them, but you don't need to copy them down into your notebook. The replacement set is a set of numbers from which replacements for a variable may be chosen. So they are possible solutions, whereas a set is a collection of objects or numbers often shown using braces. We talked about braces in one of the other videos. Basically, they look like wiggly parentheses. An element is each object or number in the set, and a solution set is the set of elements from the replacement set that makes an open sentence true. So if I have a replacement set, I have a whole bunch of numbers that I can try to plug in for my variable. If any of those numbers make the statement true, they are part of the solution set. Solution sets can be one element big, where there's only one possible solution, or they can be true for all real numbers, or some combination. So let's keep going. We're going to practice. We're going to solve each equation here. And our first equation looks like this. Please write it in your notes, and we're going to talk about it. When I'm looking at this first equation here, there are two different ways that I can address this problem. The first way that I want to do it is I want to think about order of operations, and I want to simplify inside my grouping symbol. Well, if I'm thinking about order of operations, inside this grouping symbol, I'm going to start again with order of operations, and I see an exponent. So I get 4, take away, well, 2 squared is 4, plus 5. All of that stays inside my grouping symbol with a W. Now inside my grouping symbol, I see addition and subtraction only, so I'm going to work left to right. And I subtract first. I get 4 minus 4, which is 0. Again, it feels silly to write out all of these steps, but it gets you into a good habit when the math starts getting more complicated. I wind up with 5W equals 25. Last step here, I see multiplication. I undo multiplication with division. If I divide both sides by 5, so I'm using that property of equality, I get W equals 5. one solution, the only value that will make this a true math statement is a value of w equals 5. Well, now let's think about it the other way. We just talked about the distributive property, so I might look at this equation and decide, you know what, I want to distribute first. So if I take 4 minus 2 squared plus 5, I can use my rainbow and I want to distribute this multiplied element to each piece inside my parentheses. So I get 4 times w minus 2 squared times w plus 5 times w equals 25. Looking at this, my next step, well, 4w stays the same. 2 squared is 4w plus 5w. Left to right, addition and subtraction, I get 4w, take away 4w, well, that goes away. I get 5w equals 25. And same thing as I had here, my last step is to divide both sides by 5, and I get w equals 25. Either way works, I get to the same answer, roughly the same number of steps. If I were diving into this problem, I would solve it this way, but both ways are correct. Let's look at another one now. I have this next equation. 6k plus 3 times 10 minus 8 equals 2 times 3k plus 22. Well, first thing I'm going to do is I'm going to deal only with the left half, with my expression on this side of the equal sign, and I see a grouping symbol to deal with. So I take 3 times 10 and I'm going to leave that side alone for a minute here. I want to simplify my left-hand side of the equation. When I get this here, well, now I'm down to addition and subtraction. 6k plus 22. These are not like terms, so I'm done. There's nothing else I can do to simplify this expression. So now let's take a look at the other side of our equals sign. I have 2 times 3k plus 22. This really is just multiplication and multiplication. There's not really a need for a grouping symbol, but we can address this part first. 2 times 3 is 6. 6k plus 22. Well, if I look at this here, this side, not 222, there we go. They wound up identical. But let's say we didn't notice that yet, so I'm going to keep going with my simplifying now. I have variables on both sides, and I want to get them on the same side of the equation. So to get them on the same side of the equation, I'm going to take away my 6k from this side. I'm going to take away 6k from this side. Well, that leaves me with 22. 22. At the end, when I've simplified both of my expressions and I've used my properties of equality, I wind up with 22 equals 22. Well, that's an identity. At this point, I know that no matter what I put in for k, 22 is always going to equal 22. So k could be 10,000, k could be -4, k could be anything. Any real numbers would make this a true statement. So my final answer is that the solution set is all real numbers. Last year in math, you might have called that infinitely many solutions, which is also true. So the solution here is all real numbers, because no matter what I do to k, 22 will always equal 22. So now let's look at one last practice problem for this type here. And remember, you should be writing these problems in your notes and showing all your steps to solve them. Now I have 2d plus 2 cubed minus 5 equals 10 times the quantity 5 minus 2 plus d times the quantity 12 divided by 6. First step here, I have a grouping symbol, and inside my grouping symbol I see an exponent. So I'm going to get 2d plus, well, 2 to the third is 8. Inside my grouping symbol. We're going to leave this side alone. We're going to deal just with this side for now. And again, I see grouping symbols. I want to keep going. I get 2d plus 8 minus 5 is 3. And I'm done. There's nothing else I can do to simplify this side of my equation. On this side here, well, let's deal with our grouping symbols. We've got two separate grouping symbols. First one is 10 times, well, inside my grouping symbol, I have 3 plus D. Inside my grouping symbol, I get 2. I'm going to continue here. 10 times 3 gives me 30. D times 2 gives me 2D. Now I want to get my variable on the same side of the equal sign, so I'm going to take away D, 2D from both sides. But when I do that, well, now I'm left with just 3 on this side, and I'm left with 30. 3 does not equal 30. Does not equal. So at this point here, I know that there is no solution. There are no values that would make this a true statement. No matter what I put in for D, 3 is not going to equal 30. So at this point, I can say that there are no solutions. No real values for D will make 3 turn into 30. So we saw all 3 types there. We saw one where the solution set was one single value for our variable. We saw an example where the solution set was all real numbers. And we have an example of what the solution set looks like when there is no solution. There are no values for the variable that make that a true statement. We're going to do 2 more quick practices with this here, using a different type. We're going to determine if the given number is a solution. So now, instead of trying to find what the solution is, I want to determine if a given value is part of that solution. That could mean that it is the one and only solution, or it could mean that all real values are the solution. This first one here, I'm going to use my skills of substitution. Wherever I see x, I'll plug in a -6. So I want to know, does 10 equal 1/2 times -6 minus 7? Order of operations. When I combine all these terms and I get down to my last space here, I have 10 equals -10. Well, that's not true. 10 does not equal -10. So x equals -6 is not a solution. Now, if I look at this expression here, there is a solution. It just doesn't happen to be -6. Next one I have here, I want to do the same process. I have y equals 24. I'm going to plug it in for y. And I want to know, does 24 minus 3 equal 4 minus 1 times 7? So on this side, I simplify it down to a single term. Does 21 equal, well, 4 minus 1 is 3 times 7. And 21, does that equal 21? Yes, it does. So my final answer is y equals 24 is a solution, and in this case it is the only solution to make this a true statement. Lots of practice problems. This is a tricky skill. Remembering how to substitute in is something that you will need to do all year long. So, your job now, after you finish this video and you have your notes written, is time to think about the homework. On this one here, your homework task is from 2 separate pages in the textbook because we had 2 skills that we squished together. On page 29, you're going to do 3 through 45, the multiples of 3. That means 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45. Multiples of 3. Then on page 36, you're going to do 43 through 46, 54 through 56, and 71 through 74. That winds up being 26 problems. But again, most of these are pretty quick. I promise that not all of your homework assignments all year long will have this many problems. You just got to get through a whole bunch in the beginning so that I know that you are set up for success. If you're done watching this video, you should have your whole page of notes, or 2 pages of notes. You should have 1.4 and 1.5, and you can get started on your homework task.